Hi, today we're going to talk about equilibrium. So to start out, we're going to talk about basically what equilibrium is. So when you have chemical equilibrium in a system, that means that all the concentrations in a system are constant. And it's important to realize the difference between what constant means and what equal means. So if something is equal, that means all the values are the same. If something is constant, that means the values are no longer changing. So we'll look at some graphs in class and some examples of this so you can kind of see the difference. When you have something called dynamic equilibrium, it means the rate of the forward reaction and the rate of the reverse reaction are equal. So now when we're looking at reactions, we're not really thinking of a reaction that goes to completion. We're thinking of it a reaction as going in two directions. So it's going in the forward direction and it's going in the reverse direction, but we're kind of looking at the relative rates of those, and when those rates are equal, that means that that system is in equilibrium. So if you look on this example here, you can see that once it reaches equilibrium, these lines on the graph no longer change. So HI is your reactant. HI is your product and H2 and I2 are your reactants. So you can see HI when it starts out is 0, but as the H2 and the I2 start to react, you start to get HI produced. Once you've reached a level where they're no longer changing, so no more H2 or I2 is being used up, no more HI is being produced, that's when we say that system has reached equilibrium. So the values are not equal to each other, but the values are at a point where they're no longer changing. Okay, so the next thing we want to look at is something called the equilibrium constant. So the equilibrium constant is a ratio of the concentrations of the products raised to their coefficients divided by the concentrations of the reactants raised to their coefficients. So this is something that you can set up for a system that's at equilibrium, and then you can solve for this constant. There's something called the law of mass action, which all that means is that's looking at the relationship between a balanced equation and this equilibrium expression. So we're going to learn how to set those up. So this is an example of how to set up either a Kc or a Kp. So again, a K is the equilibrium constant. We'll get to the point where we don't really specify Kc's versus Kp's, and as we go through these next couple chapters, we're going to look at a lot of different K values, like there's Ka's, Kb's, KSP's. We'll get to all those later, but for now we're just going to deal with these initial ones. Kc is what you would use when you're setting up an equilibrium constant expression for things that are given in molarities. A Kp is something you would use to set up when you're using an expression for a system that's giving you the units as gases. So it's just a little different notation, but overall it's the same idea. So if you look at how that matches the equation that's given, it's always products over reactants. So notice the products are on the top, the reactants are on the bottom, and then it's whatever the substance is raised to the power of the coefficient. So here's the substance raised to the power of the coefficient, and it follows all the way through. Now when you're writing it for a pressure, instead of substituting in the actual substance like you would over here if it was a concentration, you write P and then you write the identity of the substance on the bottom. And again, we'll go through examples so you know what that means, what that looks like. Okay, so this is one where we could set this up. And what we're going to do is it says to set up an equilibrium constant. I'm going to show you both ways to set it up as either a Kc or a Kp so that you can see that it's the same thing, but it's just kind of a notation difference. So if I was going to set this up as a Kc, I would say Kc equals products over reactants. So CO raised to the power of the coefficient's 1, so I don't need to write it. H2 is my second one, raised to the power of the coefficient, that's where that 2 came from, over reactants, CH3OH, raised to the power of the coefficient, which is 1. Okay, so if it asked for a Kc, that's how I would set it up. If I was going to write this as a Kp, again, same idea, just a little bit different notation, I would write PCO, And if you want to put them in brackets, you can. Sometimes people put them in parentheses. It's completely up to you on that. Then I'm going to do pH2 raised to the second over pCH3OH raised to the first. Okay, so again, same idea, just a little variation in the notation if you're writing a KP versus a KC. And as we work through these, you'll kind of see the difference here. So once you have a K value, what this K value can tell us is which direction equilibrium lies when you have a reaction at equilibrium. So if K is less than 1, if it's a number that's really, really small compared to 1, that means the reverse reaction is favored, which means at equilibrium for that particular reaction, there's more reactants than there are products. So it means the forward reaction, which would be making products, doesn't proceed very far. If K is about equal to 1, then that means that neither direction is favored, so the forward reaction proceeds about halfway. If K is much greater than 1, then that means the forward reaction is favored, and that forward reaction proceeds pretty much to completion. So you would use this if you're running a reaction and you're trying to produce something. If you have something where that K value at a particular set of conditions is very small, it's not making the reactant. So what you can do then, we'll learn later on, is you can do things to these reactions to actually shift them so that it proceeds in the direction you want it to. So for this particular one, if you solve for K and it gives you a large number, it would tell you that most of the reactants have been converted to products in this case. And another way to say that is sometimes we'll say equilibrium lies to the right or it lies to the left, depending on whether it's reactants or products. So in this case, since it's lies to the right, mostly we would say it lies to the right because it's mostly products that are being produced. This particular one, if K is a very small number, then when we would say that K lies to the left. So if you notice there's not very much product produced, most of what's in that equilibrium mixture is reactants. So the other thing we can do is if we have a K and we have a chemical reaction, we can actually manipulate K by using a couple rules. So this is kind of similar to what we would do with the delta H value. So if you remember when we talked about Hess's law, if you had a delta H value for a reaction and you flip the reaction, you flip the sign, and then if you added a bunch of reactions up to get the overall delta H, you added them up. Okay, this is same idea but very different rules. So for the K value, if you reverse a reaction to get a new K, you invert the equilibrium constant, so you take 1 over. If the coefficients are multiplied by something for a K, then you raise the equilibrium constant to that factor. So say you multiply all the coefficients by 2, you take the K value and you raise it to the second power. If you add 2 or more equations together to get an overall equation and a K for the overall equation, you multiply the equilibrium constant instead of adding like you would for a delta H. So again, same idea, we can manipulate the equation and manipulate that constant, but it's very different rules than what we did for the H's. All right, so let's look at a couple examples here. So for this one, it gives you an initial reaction, and these are all going to give you temperatures because they're all temperature dependent. We'll talk about that as we go through. So for the reaction here as written, this is my K value. The other thing to notice here is now notice how we're no longer just using a single arrow. Now we have a double arrow that shows that this reaction could actually proceed in either direction. So if this is the K value for the reaction as written, now we're going to compare this new reaction to what we originally had to see if we can figure out what's been done, what's been manipulated, and then figure out the new K. So if we look at this reaction down here, we can see that first of all, it has been flipped. So it's been flipped so that what was originally the products are now the reactants. So for a K, when you flip something, you know you're going to have to. So K, we're calling this K prime here. So to get K prime, we know the first thing we're going to have to do is take 1 over K because I flipped it. Okay, so flipping is 1 over. Then the other thing, notice the coefficients were all divided by 2. So again, instead of dividing the K by 2 like I would have if it were an H, I'm going to raise this to the 1/2. So to get the new K, because I flipped it, I'm taking 1 over. And because I divided all of the coefficients by 2, I'm raising it to the power of the 1/2. So then I would take 1 over the original K, that 5.6 times 10 to the 5th, to the 1/2. So my new K, my K prime would be 1.3 times 10 to the -3rd. The other thing that's kind of different about K is there are no units for this. So we had all those crazy units for lowercase k, which was the rate constant. This K value has no units. So for these, you don't have to worry about units, which is nice. So for this one, this would be my answer, 1.3 times 10 to the -3rd. Okay, another thing we can do is we can look at the relationship between Kc and Kp. So depending on the reaction, sometimes the two values are the same. Sometimes they're a little different depending on what is present in a particular situation. So if we look at the relationship between these, there's a reaction or an equation we can use. So Kp is equal to Kc times RT delta N. So Kp, like we talked about before, is the equilibrium constant with respect to pressure. Kc is the constant with respect to concentration and molarity. R is an ideal gas constant, but notice this is a different R than what we used in the last unit. So this one is different. It's the same constant, but it's given with different units, so that's why the numerical value is a little different. So this one we're using that 0.0821 liter atmosphere per mole K. Temperature still has to be in Kelvin. And then to get that delta N, you take the moles of gaseous product minus the moles of gaseous reactant. Okay, so again, basically you're just plugging these numbers in, but you got to make sure you know what all those different things mean. All right, so let's look at an example for this one. So this one gives us an equation, and it gives us the Kp value for that equation. So now we're going to look at Kc. And like I said, sometimes Kc and Kp are the same. It just depends on how many moles of gas are present. So for this one, I'm going to use Kp equals Kc RT delta N. So I'm going to make a list of my variables off to the side here. Kc is what I'm trying to solve for. Kp is given 2.2 times 10 to the 12th. And again, notice it has a temperature associated with it. So for now, we're going to assume that the temperature stays constant. Later on, we'll talk about how to deal with it when the temperature changes. R is the ideal gas constant, 0.0821 liter atmosphere per mole K. Temperature has to be in Kelvin. So they gave me the temperature in Celsius. I'm going to add 273 to get to Kelvin. So my temperature in Kelvin is 298. And then to get my delta N value, I'm going to take moles of product minus total moles of reactant. So moles of product is 2, and then for my reactants I have 2 plus 1, so I'm going to take 2 minus 3. So moles of product minus moles of reactant. So my delta N is a -1. That negative is really important here. So you got to make sure you always do products minus reactants, because the sign of that value is going to make a difference in what this final answer is. Okay, so then if I plug everything in here, Kp, I'm going to get rid of that, replace it with the value. So Kp is 2.2 times 10 to the 12th equals Kc 0.0821 times 298, and I'm going to take all of that to the -1. So you can almost think of this like all of this together to the -1, and then rearrange it to solve for Kc. So in this case, Kc would be 5.4 times 10 to the 13. Again, K doesn't have a unit. The other thing we can look at on this one, if we look at how large that K value is, that means the equilibrium lies to the right. So for this one, most of those reactants are being converted to product. So a lot of product is being made for this one, and we know that because of that really large value of K. Okay, last thing to look at when we're talking about setting up those K expressions is looking at something called homogeneous equilibria versus heterogeneous equilibria. So homogeneous equilibria means all the reactants and products are in the same phase or the same state. So they're all aqueous or they're all gases, etc. Heterogeneous means you have one or more reactants or products that are in a different phase. If you have something in a pure solid or pure liquid phase, you don't include that in the equilibrium constant expression. And that's because if something is a pure solid or a pure liquid, no matter how the equilibrium shifts, the concentration of it doesn't change. So we leave it out of the expression. If you have things that are gases or aqueous, those concentrations can be affected, so that's why we leave those in. So again, an example on this one. So if I was going to set up Kc for this, I would take products over reactants raised to the power of the coefficient. But for this one, again, if it's a solid or a pure liquid, it's not included. So this would not be included in the expression, and this would not be included. So this one, the only thing I would have would be CO2 raised to the power of 1, which I don't need to write. So this would be the equilibrium constant for that particular equation. So again, you only include gases or aqueous solutions. Solids and liquids, pure solids and pure liquids, are not included. Okay, last thing to talk about here is how to calculate the equilibrium constant. Now we're only going to look at the easiest way today, and then tomorrow we'll come back and look at ones that are a little more complex. So the easiest thing, or the easiest way to do this, is if we know all the concentrations in equilibrium. If you know all the equilibrium concentrations, then all you have to do is plug them into that K expression that you set up. So that's the one we're going to look at today, and that's where we're going to stop today. But then tomorrow or the next day we'll come back and look at how you deal with them if you don't. So for this one, it gives me the overall equation. So before I'm going to do anything, I'm going to set up my K expression. So K, and for this one, if it doesn't specify, well, it does say Kc, so we'll label it as Kc. So I'm going to do products over reactants. These are all gases, so these are all going to be included. So I would put NH3 raised to the second power over N2 times H2 raised to the third power. Again, products over reactants raised to the power of the coefficient. So now all I have to do is, if you notice in the problem, it tells me what the equilibrium concentrations were. So it said the equilibrium mixture of gases was analyzed. This here is really important because you can only do this if you have the equilibrium concentrations. So it tells me it has this much H2, this much N2, and this much NH3. So all I have to do here is plug those values in. So I'm going to do 0.00272 squared over 0.0403 times 0.1207 raised to the third power. Solve that, and I get 0.1044. So that's my Kc value for this one. Now for this one, since Kc is a small number, that means that there's not very much product being produced. So we would say equilibrium on this one lies to the left. There's more product or more reactant present at equilibrium because of that small value of K. Okay, so see what you can do with your homework problems at this point, and we will come back to all of this. I realize we have the lab when you guys after study hall, so we'll do the lab, and then we'll come back to all this, and we'll look at how to deal with these when you don't have all the values.